Welcome to this lecture series in group theory. We are starting a new module which will be about group actions. Perhaps this and the next module will be about group actions. So let's get started. So, what is a group? Philosophically, a group is supposed to be the set of symmetries of some abstract object or some object hidden from us. What we would like to do is realize a given group as the set of symmetries of some concrete object. All right, so that might give us some information about the group if we can indeed realize the group as the symmetries of some object that we understand. So this philosophical statement motivates the following definition. So we will define, or we may define, it's not the final definition, but we may define an action of G on a set X is an embedding of G in symx. And recall, an embedding is an injective group homomorphism. So how does this capture the philosophy? Because if we have an injective homomorphism of G into symx, then every element of the group G can be seen as a permutation of X, so a symmetry of a concrete object. And that's how it is capturing the philosophy here. However, it is of great use to relax this definition, this preliminary definition, which I will put in quotes a little bit. And here is our formal definition. So we define an action of G on a set X as a homomorphism from G to symx. So that's our definition of an action of a group. So this may lose information. For instance, the map which takes everything to the identity permutation is also an action, and it is not telling us anything about the group, right? So this may be lossy, but still, it is, at least if it is not completely lossy, it is telling us at least something about the group. So that's our definition, and of course, it may not be clear as to why such a thing is even useful, why this definition is useful, but it is of great importance and use and utility in the study of group theory. Many non-trivial results can be proven once we develop the sufficient machinery around this concept. All right, so we will look at examples. We will look at a lot of examples in the course of this module and the next. But in this lecture, we will look at only a few. And before we get there, we should look at a few other things. So let us define the kernel of the action. So given an action, suppose we are given an action of G on the set X. So basically, we are given a homomorphism from G to symx. We define the kernel of the action as the kernel of phi. So this is called kernel of the action. Not at all a surprising definition. And what is this measuring? This is measuring how lossy this is. So how much information we are losing in this concrete representation of the group G. Right, so that's it. I mean, this had to be said, so I have said it. Great. There is a alternate way to look at a group action, and that is actually a very important way. So now let's do that, and then we will look at examples. So fix a group G and X be a set, and fix an action of G on X. Then we can define a map of this sort, G cross X to X, as phi of G comma X is the permutation phi G applied on X. All right, so this is how we define our map capital phi using the map small phi. And we write, instead of writing that, we will be writing G dot X. Of course, one should remember that this dot is actually referring to this capital phi. So of course, if there were some other phi, instead of phi, suppose we had some other action psi of G on symx, using dot to denote both of them would be, or rather using dot to denote the corresponding these guys for both of them would be confusing. So one has to remember, under this convenient notation, one also pays a price that one is forgetting the exact meaning of these things, but most of the times there is no confusion. Okay, so there are some properties, or at least I would say two properties that we want to look at. So first we notice that E dot x, where E is the identity of the group G, E dot x is what? E dot x is phi E of x, but since phi is a homomorphism, phi E is the identity permutation, and therefore this is x. So we see that E dot x is x for all x. And the second property is G1 dot G2 dot x. What is this? This is phi G1 operated on G2 dot x. What is that? That is phi G2 operated on x, which is nothing but phi G1 composed with phi G2 operated on x by definition of the composition. But now by the group homomorphism property, this is phi G1 G2 operated on x, which is G1 G2 dot x. So here we are applying successively G2 and G1. Here we are first operating G1 and multiplying G1 and G2 in the group G, and then operating the result on x. So what we note is that the second property says G1 dot G2 dot x equals G1 G2 dot x for all G1 and G2 in the group G and x in the set x. So we notice these two properties of this map. All right. Now conversely, suppose we have such a map. Suppose we have a map such that the two properties hold, meaning E dot x is x for all x, and G1 dot G2 dot x is G1 G2 dot x for all G1 G2 in G and x in x. Again, E dot x really means phi E comma x, capital phi, and this let me write that down. So this is nothing but phi G1 comma phi G2 comma x, and now we appreciate why we resorted to the simple notation. All right, so suppose such a thing is given, we will create an action of G on x. So with that information, define little phi going from G to sim x as phi of G. Now we need to define phi of G. So given little g in capital G, we need to define phi of G. So how do we define it? It picks up some x, and what does it output? It outputs G dot x. So that's our definition of phi G. And therefore we have defined a new map phi. Now it is not clear that it indeed lands inside sim x. As of now, it is only landing inside maps from x to x, right? That much is clear. Phi G takes an element of x and produces an element of x. So definitely it's a map from x to x. But we need to show that this is actually a bijection. So why is it a bijection? Suppose phi G of x1 equals phi G of x2. Or let me say, if then, let me write then here, then it just means that G dot x1 equals G dot x2, which implies G inverse dot G dot x1 equals G inverse dot G dot x2, which implies by the second property, G inverse dot G, or okay, I shouldn't write a dot here, G inverse G dot x1 equals G inverse G dot x2, which implies E dot x1 equals E dot x2, which by the first property implies x1 equals x2. Right? So this is injective. Phi G is injective. And I leave as an exercise for you to show that phi g is also surjective. If you assume that X is finite, then of course injectivity of phi g implies the surjectivity of phi g. But in general, it does not. So surjectivity of phi I leave as an exercise. And therefore, we indeed have a map from G to sim X. So now we need to verify the homomorphism property. So to do that, we have phi G1, G2 of X is by definition G1, G2 dot X, which is G1 dot G2 dot X by property 2, which is by definition of little phi is phi G1 of phi G2 of X, which is phi G1 composed with phi G2 operated on X by definition of composition. And that's it. That proves that phi G1 G2 is phi G1 composed with phi G2, and hence this is a homomorphism. So basically, what we are trying to say is that there are two perspectives in which you can view the notion of an action. Either you define an action this way, that it is a map from G cross X to X with these two properties, or you define this way, that it is a homomorphism from G to sim X. One should be comfortable with both perspectives, and one should be able to move from one perspective to the other very easily. So both are important. One cannot ignore either of them. This is a natural one. This is how we arrived at the notion of an action. We just had a philosophical idea and we formalized it and reached here. So this is a natural way to define actions. But this is so useful that many textbooks just start with this. All right. So now let us look at examples. Any abstract definition should be understood via examples. So we will look at some simple examples in this lecture, and as we go along, we will look at more and more complicated examples and the consequences of them. Okay, so our first example is the simplest one, that Sn, the group of permutations of the first n integer, acts on this. How? What is the action? So just send Sn to Sn, which is nothing but sim of the first n things, identity map. So in the first perspective, this is your action. This is G, and this is X, right? Making it ugly. So yeah, I should explain this. So when a group acts on a set, we notate it in this fashion. So suppose we are given an action of a group G on a set X, we write G and then we make this arrow and write X. And of course, this just means that G acts on X. How exactly it acts, that information is here in the map phi. So this of course suppresses this whole information. So when we write this, we just mean that there is some homomorphism of G to sim X given to us, or we have some map of the sort G cross X to X, right? So when we write that, we just mean that such a thing is given. And here when we write this, we just mean a specific action which we are defining. So this particular action, this is the group acting on this set, and the homomorphism is just the identity map. In the second perspective, the map is Sn cross 1 to n going to 1 to n it just takes a group element, let's call it sigma, and a letter I sends it to sigma of I. So these are the same things. This perspective and that are this description and those description are the same under the equivalence that we discussed previously. So this is how Sn acts on the first n integers. Right? You just pick a permutation and hit any given letter by that permutation, and that's how it permutes things here. That's a pretty trivial action in some sense, or pretty simple action, or not a very interesting one, or whatever. Cousin of it is this. So instead of the first n integers, we have replaced that by some arbitrary set, and simx acts on that. How? Just the identity map. And I encourage you to write down the description of the other perspective. All right, this is a somewhat more interesting one. Suppose A is just some set, some alphabet as you might want to think about it, and Sn is that guy. Then we will define an action of Sn on that guy, A to the n. And what is the action? I think the second perspective is much cleaner here. So Sn cross A to the n going to A to the n what is this map? This map just takes sigma and an n tuple and gives us the permuted tuple. Right? So that is our action. And one can verify easily that this is an action. If this were the identity permutation, then of course this is mapped to itself and you can verify the other property. So that exercise you must do and try to look at in this perspective also, the homomorphism perspective. Okay. This is a very nice thing. Again, in some sense a trivial one, but it just says that the group of linear endomorphisms of Rn acts on Rn. You can think of this as either a group of matrices, n cross as an invertible matrices, or the group of invertible linear endomorphisms, whichever perspective you prefer. Let me think of these as invertible linear endomorphisms. So how is this action defined? The action is so we have a map T and a vector V. It just goes to the image of the vector V into the linear map. And one can again check that this is indeed an action. If this were the identity transformation, the identity of this group, then of course V would give us V, and you can verify the second property. So that's a nice action, and this is sort of a cousin of the above one. Here we are deleting the origin, and we want to say that this also gives us, we can also define an action here. So what is the action? The same one as in the previous. So it takes T comma V to TV. The point is that since these are invertible linear maps, a non-zero vector has to map to a non-zero vector under any invertible linear map. So the action kind of restricts to this guy. The above action restricts to that. Okay, and this is a abstract example. Suppose we are given an action of G on X and we are given a subgroup of G. Then we naturally get an action of H on X. And here the first perspective immediately comes to the rescue. We are given an action of G to G on X, so a homomorphism from G to sim X is given. We have this inclusion map, and we just compose to get another homomorphism. So this is how we get an action of H on X, right? So very nice. Now let us look at a very nice concrete example. I borrowed this from a YouTube channel by Professor Macaulay. It is the name of the channel is also Professor Macaulay, and the course he is teaching is named Visual Group Theory. He gives a lot of very nice visual examples throughout the course, and I highly recommend you look at his lectures. This is lecture 5.1, in which he discusses group actions. So lecture 5.1. Oops. Okay, let me get rid of that. So lecture 5.1, you can check that, or you can just check out his whole course. It's a very nice course. All right, so we have the dihedral group on four letters. So it's the symmetries of the square of the the Euclidean plane. So this is how we drew it in our discussion. So we had this. We had these coordinate axes, and we defined rotations and reflections and their composites as this D4. So recall the definition of D4, and we will define an action of D4 on this particular set. What is this set? This set is just like, you have tiles. So this is the first tile, this is the second tile, where so every tile is kind of like a 2x2 grid, but here all the things are colored orange. Here 2 of these are colored blue, 2 of these are colored orange, and so on. And we will define an action of D4 on this set. So D4 is generated by two things: anti-clockwise rotation by 90 degree and reflection by the x-axis or the horizontal line. So just to make a mental note, this is rotation by 90 degree in the anti-clockwise sense, and this is reflection by the horizontal line. Okay, so what happens if we hit that, rotate, actually physically rotate this guy by 90 degrees anti-clockwise? We get this thing back. So I will draw an arrow like this and write R here. And what happens if we reflect this thing by this about this axis, we get the same thing back. So I'll write that. And when I make these arrows, I just mean that r dot this orange thing is this orange thing, and s dot this orange thing is this orange thing. So that's what these arrows mean. If you start with this and apply r to it, meaning dot it with r, you get this guy back. And if you start with this and dot it with s, you get this thing back. So that's the definition. Okay, so what happens if we rotate this by 90-degree anti-clockwise? You get that guy. Okay, and what happens if we rotate this 90-degree anti-clockwise? We get that guy. So we may just delete this arrow. Basically, you can just keep switching between this and that if you keep rotating by 90 degrees. And what about reflections? If we reflect this guy by this axis, we get that. And if we reflect that, we get that. So I'll also join it by a red edge. Okay, what about this? If we rotate this by 90 degrees anti-clockwise, we get that. So here we get an arrow. Oops. Rotate that by 90 degree, we get that. And similarly this and that. So this is a very nice cycle that we see. You keep going in this cycle if you keep rotating. What about reflecting? If we reflect it about this axis, we get that one. So I should have used white color. I somehow used yellow or pink color. So what about reflection? If we reflect this guy by this axis, we get that. So we join it by this edge, but if you reflect that guy about this axis, you get back to the original one. So we are not drawing an arrow here. What about this? If you reflect about this axis, you get the same thing back. So this is a loop and that is also a loop. So this is how we define an action. Writing this out in a formal way is not going to help. This diagram is much more helpful. And this is how Professor Macaulay explains it. So yeah, so this is a very nice example of an action, a non-trivial example of an action. The examples that we see were kind of like trite, but anyway. And we will look at a lot more examples and applications, and the course kind of really begins here, you could say that. All right, so as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.